Welcome back, students. In the last chapter, we discussed how we can use entropy to determine when a process is natural, and by natural, we mean spontaneous. To do this, we had to calculate the entropy of the system and the surroundings and add the two. If the total change in entropy was positive, the process will occur naturally or spontaneously. What we're going to do in this section is go into a more familiar way to determine spontaneity. And what we're going to do here is attempt to group these two terms, the entropy of the system and the entropy of the surroundings, group those together to get something that's based solely off the system properties. And you're familiar with what this is. We are going to derive the Gibbs free energy today. So the goal for today is going to be to learn about the Gibbs and the Helmholtz free energies. So we're going to state the motivations for using the Gibbs and Helmholtz energies, which we just did. We're going to then explain why we use the Gibbs free energy and not the Helmholtz free energy. This is the exact same reason we use the enthalpy more commonly than the internal energy. And then at the end of class, we are going to look at these relations called the Maxwell relations, named from James Clerk Maxwell. And what these are a relatively complex looking set of partial derivatives, and they do the same things that we've been doing with all of our partial derivatives. So they allow us to take partial derivatives that we might want to know what they are but can't solve and find them in terms of things that we can measure experimentally. So we'll go into that in the last few minutes of our lecture today. Just like in the past few lectures, we're going to be doing a lot of derivations, so we're going to go to the board. To start our derivation today, and remember the goal here is to figure out the Gibbs free energy so we can figure out spontaneity based only on the system properties, we're going to need to start with our Clausius inequality. And this is the same condition that we had last time. So our condition for spontaneity previously was that the change in entropy for the system plus the change in entropy for the surroundings must be greater than 0. So if entropy increases overall, then this is a spontaneous process. This is another form of the Clausius inequality that we saw. We can derive the Clausius inequality from this and show that the two are related by considering the differential forms of this. So the differential form of our delta S for the system is ds, and delta S surroundings is simply ds surroundings over t. ds surroundings is negative dq surroundings. So we can say that we have ds plus the dq of the surroundings over t, which is equal to ds minus dq for the system over t. And then we can rearrange this, and this is all has to be greater than 0. So if we multiply by t and add dq to the other side, we get t ds is greater than dq. And this is our Clausius inequality. So from here, what do we do? Well, what we're going to do is represent our derivative of heat here in terms of the total energy. The reason for doing this is because the change in internal energy of the system is equal to the negative change in internal energy for the surroundings. This is also true for volume. So d volume for the system is equal to negative d volume for the surroundings. As we can see up here by our inequality, this is not true for the entropy. So ds does not equal ds surroundings. So what we're going to do is rewrite basically ds surroundings in terms of du surroundings, dv surroundings, things like that, and then we can relate those to the system. That's kind of the idea about what's going on here. So what we can do is say that dq is equal to du minus dw. This is the first law of thermodynamics, where we say that the internal energy change is equal to the heat plus the work. We can expand the work as follows. So we can say that our internal energy is still du, but our work here is negative p external dv. And we're also going to now include a term for non-expansion work. So we still have this non-expansion work. This is going to be important for the Gibbs free energy. Then what we can do is plug this here into our dq and bring them all over to the same side of the equation. So what this will get us when we do that is negative du minus p external dv plus the non-expansion work plus TdS is greater than 0. So note at this point that we have successfully removed the surrounding component. We have only properties of the system here. We can condense this to make a very nice form. What we're going to do is consider isothermal processes. Those are the kind of processes that we normally consider. And recall that the process doesn't actually have to be isothermal. What an isothermal process means is that the start and end are at the same temperature. So if we have a chemical reaction that raises the temperature, if we let it cool back down to the starting temperature, we have an isothermal process. So if we have an isothermal process, what we can do is say that TdS is equal to dTs if the temperature is not changing. This will allow us to group it in with du. So what we're going to do is take these work terms and bring them over to the other side of the reaction. So we'll have negative du plus dTs is greater than P external dV minus the non-expansion work. Then we are going to divide by -1. And if you probably haven't done inequalities in a while, but if we divide by -1, we have to change the direction of the inequality. So if this inequality up here is true, then the following du minus dTs is less than negative P external dV plus the non-expansion work. And then what we can do, since we have two derivatives here that are added, we can actually group them. So du minus dTs is equal to du minus ts. And what we'll do is define this function u minus ts as a new state function, and we'll give it the symbol A for the Helmholtz energy. So what we're saying here is that dA is always less than negative P external dV plus the non-expansion work. And what you'll note is that this is the expansion work plus the non-expansion work. So we have this state function A, this Helmholtz free energy, that is always less than the total amount of work that is possible. And here I'm using this strictly less than. In some cases, you'll see, like we talked about for entropy, less than or equal to, where it is equal to the work for a reversible process. But for all non-reversible processes or irreversible processes, which are every process we can actually do, it is less than the work. We considered to get this far in our derivation that we have an isothermal process, but the Helmholtz free energy is also particularly applicable if we have a constant volume process. So if we have a process at constant volume, there is no expansion work. And we can also consider processes that have no non-expansion work, such as normal chemical reactions. So if this is also 0, for a constant volume, constant temperature process, we have arrived at the expression that dA is less than 0. So remember, this inequality that we have here is meant to determine natural processes. So going back up to the top, this Clausius inequality says for all naturally occurring processes, TdS is greater than dQ, and we were able to get that delta S of the system plus delta S surrounding has to be greater than 0. So this is the same thing down here. For all naturally occurring spontaneous processes, the change in Helmholtz free energy is less than 0. What we've noted here is that this Helmholtz free energy, much like the internal energy, is especially applicable for constant volume scenarios. In chemistry, we don't often have constant volume scenarios. We're typically working under constant pressure conditions, say on the bench or under a hood. In this case, what do we have? Well, we'll use the same inequality that we have up here. So we will take, we'll take this guy and evaluate this under constant temperature and constant pressure conditions. So our constant temperature conditions give us the same TdS equals dTs, but our constant pressure conditions will give us that P external dV is also equal to dPV because the pressure is constant. And so in that case, what we'll end up getting is the following. We'll have that du plus P or dPV minus dTs is less than the non-expansion work. And this all I did is enforce the condition that P was constant into this equation up here to derive this one down here. We can then group these things together and say, well, now we have du plus PV minus TS is less than the non-expansion work. And what is that? Well, u plus PV is h, so now we have a new state function where u plus PV minus TS is equal to h minus TS, and you're familiar with this. This is our Gibbs free energy. So we'll say here that dg is less than the non-expansion work. And if there is no non-expansion work, it is less than 0. If no non-expansion work is possible. So we can do a couple of things with our Gibbs free energy. One, we can say, okay, if there's no non-expansion work, then if I have a negative change in Gibbs free energy, I will have a spontaneous process. And that is a common way in which we'll use this, and you used it this way in the past. Another interesting thing we can do is the Gibbs free energy for a process informs us on how much non-expansion work is possible. And you might be a little bit confused because we haven't really worked with non-expansion work in this class, but there are some important implications of this. One example of non-expansion work is electrical work. So in theory, we've talked about heat engines, and they can only convert so much of that heat into work. But in theory, we can convert 100% of work into work. Now, in actuality, you can't quite get that high, but theoretically, you can. So if we could convert or harvest the energy from a reaction in terms of electrical work, say using something like a fuel cell, we should be able to get more work out of it than if we tried to combust that and use heat. And so this is the reason a lot of people are researching into fuel cells, and we'll look at some examples of this later on in class. Another really common example of this is biochemical reactions. So something like ATP has a Gibbs free energy associated with it. And that ATP is used in the cell to do non-expansion work, such as maybe physically moving molecules. So you can think of the kinesins and so forth that are translating. You can also think about harvesting energy in terms of the proton gradient or importing nutrients into the cell. These all take or make work, and we can think about this in terms of Gibbs free energy as how they do this. We can also apply the Gibbs free energy and the Helmholtz free energy to reactions. You're familiar with this. So if we want to know the change in free energy for a reaction, we can use our definition up here and take the change in enthalpy for that reaction and then subtract T times the change in entropy for the reaction. And we could do a similar thing for the Helmholtz free energy using the internal energy rather than the enthalpy. So we have these two free energies. They're slightly different. In general, the Helmholtz free energy is more applicable under constant volume scenarios, and the Gibbs free energy is more applicable under constant pressure scenarios. And we're more commonly working under constant pressure scenarios. At this point, we have introduced the whole suite of thermodynamic energies. So we have four energies that all have the units of energy or energy per mole. The internal energy and the enthalpy are used to calculate the energy changes for reactions, and our Helmholtz and Gibbs free energies are used to determine the direction of spontaneous change and the maximum work that a reaction can accomplish. These variables are all based off of the variables like internal energy, pressure, volume, temperature, and entropy of the system. So we can now use these terms to get compact expressions for the total differentials of all of these functions. So for example, we have that the enthalpy is equal to U plus PV. And we have the Helmholtz free energy that's equal to U minus TS. The Gibbs free energy is equal to H minus Tx, which is equal to U plus PV minus Ts. So all of these terms are based off of internal energy, pressure, volume, temperature, entropy. What we're going to do is take the total differentials of these in terms of these variables. So we've seen a few times, let's think about our internal energy change. So we know that du is equal to dq plus dw. If we have specifically a reversible process, dq is equal to t ds, and dw is equal to negative p dv. And since u is a state function, we can use this for any internal energy change. So we can say that du is equal to t ds minus p dv. And we can do this for our other functions as well, since they're all based off of u. So if we have dh is then going to be equal to du plus dpv. Using the product rule, we can get that dh is equal to du plus p dv plus v dp. And then we know that du is equal to t ds minus p dv. And then we have plus p dv plus v dp. We can cancel these out and say that dh is equal to t ds plus v dp. And here we have a nice compact expression for what dh is. We can go ahead and do the same thing for the Helmholtz energy. So dA is equal to du minus dTs. And we can go and plug in our du. So this is going to give us dt or tds minus pdv coming from du. And then our dTs will give us minus tds minus s dt. We can cancel out these and say that dA is equal to minus pdv minus s dt. And finally, our Gibbs free energy is equal to dH minus dTs. And so we can say that dH is equal to tds plus v dp, and then dTs is minus tds minus s dt. We can cancel these out, and we have our Gibbs energy being v dp minus s dt. So we have these four expressions that are pooling our four energies in terms of only two partial derivatives here. Now, why are we doing this? Well, we'll focus on the internal energy, and then we'll show on this slides that you can do this for all these other ones as well. So if we have our internal energy being equal to tds minus pdv, these represent what are called natural variables. And these natural variables are simply the variables that result in the most compact expression for any of these functions. And what we note is that we're talking about the change in internal energy with respect to two functions. So we can also represent this as the change in internal energy with respect to entropy at constant volume, ds, plus the change in internal energy with respect to volume at constant entropy, dV. And comparing these two expressions, you'll note that we have the result that du ds at constant v is equal to t, and du dv at constant s is equal to minus p. And we have this pretty clear result here. We can do this for all of our functions here. Here we can see the various Maxwell relations for all of our functions. So on the slides, we talked about how to do du ds and set that equal to t and minus p. For the rest of them, we did the exact same thing. So we simply took the total differential with respect to the natural variables and said, well, what do we have this equal to on our other term? So with this, we find the following expressions. We have dH ds at constant p is equal to t, dH dp at constant s is equal to v, and so on. So we have these other ones. The important ones for us are going to be the Gibbs free energy that we're going to use further in this class, that dg dt at constant p is equal to minus s, and dg dp at constant t is equal to v. Now, something interesting comes out here in the fact that the entropy, temperature, pressure, and volume are all necessarily positive numbers. So you can't ever have negative entropy, temperature, pressure, or volume. So what that means is we can identify the direction of change for these functions. So for example, the fact that the partial derivative of Gibbs free energy with respect to temperature at constant pressure is the negative entropy means that it is a negative number. So as the temperature increases, the Gibbs at constant pressure, the Gibbs free energy always gets more negative. The slope is a negative number, the Gibbs free energy goes down. That's different for volume. So as the pressure increases at constant temperature, that's equal to the volume, which is a positive number. So the Gibbs free energy will increase with pressure. And so this is sometimes we'll bring this up to explain what's going on here. Now, the next thing that we can do is something that is pretty non-intuitive, is we're going to go into these Maxwell relations. And we're going to take advantage of the fact that we've done this before, that the mixed partial derivatives are equal to each other. So if we take the volume derivative at constant entropy of internal energy after we have taken the entropy derivative at constant volume, that is equal to the opposite. So it's equal to the entropy derivative of the volume derivative at constant entropy and then constant volume. So why are we doing this? Well, we're doing this because we know that du ds at constant volume is equal to the temperature. And we know that du dv at constant entropy is equal to the pressure. So with this, we can go in and say that dt dv at constant entropy is equal to negative dp ds at constant volume. And this is one of our Maxwell relations. Now, with this, we can interconvert between these partial derivatives whenever they come up. And we'll go ahead and look at the rest of these on the slide. Here we can see our four Maxwell relations, and just like the one we showed in the slides, these come from simply evaluating the mixed partial derivatives. So over here, we have that dH ds at constant p is equal to t, but we want to evaluate the mixed partial derivative, so we want to take the derivative of this with respect to pressure at constant entropy. So that will give us dt dp at constant entropy. We see that here. And we'll do the same thing to this side, taking the derivative of volume with respect to entropy at constant pressure. And these two are equal. And this is true for the remaining Helmholtz and Gibbs free energies as well. Now, again, to emphasize the reason why we did this, we're doing this because in some cases, these partial derivatives will appear. And these partial derivatives are not necessarily easily measurable. For example, this one here, how the entropy changes with respect to pressure. But if we can relate it to dV dt at constant p, we can use this to get it in terms of experimentally measurable parameters such as volume, temperature, pressure, and then the beta and kappa constants that we've been using. So that's the reason why we're doing this. I don't expect you to memorize any of these, but to be able to derive one, probably like the internal energy that might appear on things like homework or an exam, and then to be aware of them when we use them. Because in the future, we'll be doing some derivations, and these will pop up. And we'll go, oh, we're using the Maxwell relations. And you can go, okay, I remember we did those, and I remember the purpose is that we're relating these two seemingly different partial derivatives, but they are equal, and we can show that with the math here. Lastly here, we're going to want to evaluate how our Gibbs free energy especially changes as a function of pressure and temperature. We saw that we had our expression for dg dp at constant t, so how it changes as a function of pressure, and we saw that this was equal to v. So that means if we want to know how dg changes as a function of p, we simply have to evaluate dg dp at constant t dp, which is equal to v dp. So if we know the volume and we know how this changes with respect to pressure, we can know how the Gibbs free energy changes as a function of pressure. For gases, this is pretty easy to do. So for gases, what we can say is that delta G at T naught, and anytime we see this naught here, that's referring to the standard state. So that's the standard temperature, 298.15. So this is equal to the integral from P naught to P of V dP. Using the ideal gas law, we can say that this is equal to nRT over P dP. And so plugging in numbers here, we would get that the Gibbs free energy change at a pressure that is not the standard pressure is delta G naught, so the initial standard temperature and pressure conditions, plus this term nRT, natural log of P over P naught. So this term here will correct for how the Gibbs free energy changes as a function of pressure. For things like solids and liquids, they won't really change as a function of pressure because the volume is relatively independent of pressure. So this integral would just be the volume, and our dg won't really change as a function of pressure for solids and liquids. We'll lastly look at how the Gibbs free energy changes as a function of temperature. And we're going to do something that's a little bit shifty here. Rather than evaluating how the Gibbs free energy changes as a function of temperature, we're going to evaluate how the Gibbs free energy over temperature changes as a function of temperature. Now, why are we doing this? Well, we're doing this because eventually what we're going to want to do is figure out how the equilibrium constant changes as a function of temperature. And the equilibrium constant is equal to or proportional to g over t. So if we do g over t here, it's going to save us a little bit of time when we look at the equilibrium constant. So how do we do this? Well, we simply use the product rule. So if we're taking the derivative of g over t, we can simply treat that as the derivative of g over t. So we'll have one term that is 1 over t, so this is one of our functions, times the derivative of g over t at constant pressure. And then we'll add in our Gibbs free energy, g, times the derivative of 1 over t, our second function, with respect to t. So what does this get us? Well, we've seen using our relations up here that dg dt at constant p is simply the negative entropy. So this term becomes negative s over t. The derivative of 1 over t with respect to t is simply minus 1 over t squared. So this gives us s minus g over t squared. What we'll do is multiply both sides of this by t so we can group them. So this will give us negative, and then I'll write it in this way, g plus ts over t squared. And g plus ts is simply equal to the enthalpy. So this is negative enthalpy over t squared. So if we take the derivative of the Gibbs free energy over the temperature with respect to temperature, we find that it's equal to the negative enthalpy over t squared. Another way you might encounter this is the following. You might also encounter the derivative of g over t with respect to 1 over t. And in this case, we have to use the chain rule to go about this. So this integral is simply equal to the partial derivative of g over t with respect to t, and then multiplied by the derivative of t with respect to 1 over t, using the chain rule. And so in this case, we already know that this guy here is minus h over t squared, and the derivative of t with respect to 1 over t is negative t squared. And these derivatives are kind of scary when you're taking derivatives with 1 over something, but what you can do is treat this, again, it's another chain rule. So we're trying to take the derivative of temperature with respect to 1 over temperature. So how many 1 over temperatures is this? Well, this is negative 1, right? It's negative 1 over t. And so if we're taking this derivative, now we bring this down and just change it up one number. So we bring our negative 1 down and then increase that or decrease that by one number here to get 1 over t to the minus 2, or minus 1 over t to the minus 2, which is equal to minus t squared. So that's how we go about doing this. This t squareds will cancel, the minuses will cancel, and you'll get that this is equal to the enthalpy. And since it's nice and easy, that's why we might sometimes see it in this way. So we can integrate this expression to figure out how our Gibbs free energy is changing as a function of temperature. So if we integrate from T1 to T2 of the derivative of delta G over T, this is going to be equal to the integral from T1 to T2 of delta H d1 over t. And so in this case, I'm adding this to the over here to this side of the equation and then integrating this. We've done this kind of stuff before. This integral simply becomes delta g at t2 over t2 minus delta g at t1 over t1 is equal to delta h times 1 over t2 minus 1 over t1. we are making an assumption here that delta H is independent of temperature. If that assumption is not good, we should not make it. We'll actually have to integrate the delta H as a function of temperature. So if we assume that our starting temperature is 298, the standard temperature, we can get that delta G at some new temperature T is equal to that temperature divided by 298 times the standard delta G for the process at 298 minus the enthalpy, and then plus the enthalpy there. And this will allow us to calculate delta G as a function of T. In the next lecture, we will apply the Gibbs free energy of mixing to describe the energetics of mixing for gases. And then after that, we will use the mixing of gases to discuss the equilibrium constant and its relationship to the Gibbs energy.